Okay, thanks. Can everyone hear me? Is the mic on? Okay, great. Thank you. Okay, yeah, so this is the talk. This is joint work with Chinmay, who's at IBM. So let me just get right into it. This thing works. Okay. Okay, so let's, this is a talk about complexity, but this complexity question kind of comes from maybe a more foundational motivation of just trying to understand quantum information. So, okay, we all know like quantum states are like kind of scary. So like you've probably heard that if you have a quantum state of n qubits, this is very directional. If you have a quantum state of n qubits, it's actually a 2 to the n size vector, right? Like to describe it, you need 2 to the n complex numbers. And okay, technically it's a unit vector. So I've like said in s 2 to the n minus 1, or whatever. Okay, n is 3 for this example. But yeah, so this quantum state, has a lot of information in it, apparently, just from this description. And like, just because there's this many numbers, just by like counting, like you can see that there's no way to compactly specify all quantum states with like fewer than exponential bits, right? Just because there's this many real numbers or complex numbers here. But you might ask, like, is this really essential? Is it just like maybe we've picked a, like for physical experiments that we could actually do, like, does the 2 to the n actually help? Is there more packed into here than you could get in any polynomial number of classical bits? And one sort of example to illustrate like why this is actually a little bit of a subtle question is you might say the same story for probability distributions. You'd be like, well, okay, probability distribution on n bits. Ooh, whoops, I said qubits, but it should be bits. I also have to tell you the probability of every possible outcome for those n bits. That's also a 2 to the n dimensional vector of real numbers that lives in the probability simplex. So it's also exponentially big, right? So should we say that like randomized, randomized systems have like exponential information packed into them? Well, in some sense, yes, but also like it's often not necessary to have the full probability distribution to do useful things, right? So like often like, say you want to do something that's like do some computation on a bunch of independent samples you get from this distribution, well then you don't actually necessarily need the whole distribution. Like you can subsample and get like a much sparser representation of it that looks equivalent to your purposes. Like if you're going to take like, if you just want to compute some property of 100 samples, then you could, I don't know, like subsample 1,000,000 samples and just take the distribution that's like uniform on those 1,000,000 samples, and that would be kind of equivalent just by concentration bounds. So so this like exponentiality in probabilities is kind of fake. It's not really there in some sense. So the question behind this talk, or this whole problem really, is like, to what extent is the exponential in quantum states fake? And as complexity theorists, we're going to explore this in the following setting. We're going to ask, are there quantum states that are useful, that can do things in the context of Merlin-Arthur proof systems that no classical state of polynomially many bits could do? That's the basic question here. Okay, so now I have to define some complexity classes. So we'll start with some review, I guess, for everyone in this room. So Merlin-Arthur, as you all know, is the complexity class where you have a prover called Merlin, a verifier called Arthur. The prover sends a witness, which is polynomially many bits long. I've noted it by the letter Xi here. And then Arthur is a randomized classical machine. I've said BPP machine. Maybe that's like a bit of an abusive language. But it's a randomized machine. And so he gets this witness, and then he makes a decision on whether the input is in the language or not. So that's the class MA. Now, there are quantum analogs to this. I guess we saw one of them earlier today in Nico's talk. This is called quantum Merlin-Arthur. So this is what you get when you just take the definition of Merlin-Arthur and you make both things quantum. So now Merlin, instead of sending you poly n bits, he sends you poly n qubits, which is this? Oh, here's the pointer. Great. So, and that's I'm representing by Xi in a ket. So that's the quantum state Xi. And then Arthur is a quantum machine. Like he has to be just to process this quantum state. And he can do whatever he wants in quantum polynomial time and make a decision to accept or reject. Okay, so that's QMA. Now the third character in this story, the one that appears in the title, is the class of classical Merlin quantum Arthur, which we have very perversely chose to call QCMA and not CMQA. Sorry about that. Actually, John Watrous, when he introduced this class, called it MQA, which is, I don't know, at least makes more sense, I think, than QCMA. But yeah, this is the term that stuck. So in this is kind of a hybrid class. So here, Merlin is classical. Merlin sends poly n bits C to Arthur. But now Arthur is a BQP machine, so he can do any polytime computation. So this is the setting where we're going to try to understand, like, are there quantum states that are more useful than classical bit strings? We're going to try to understand whether QMA is different from QCMA. So if they're different, then there are problems where, there are proofs you can get or witnesses you can get that are quantum states where there's no convincing classical string that would be equivalent, right? Okay, so two complexity classes. We want to separate them. What could go wrong? Well, let's make a first observation. So we have these kind of basic containments. P is contained in QCMA. It's contained in QMA, which is contained in P space. This is not so basic, but it's true. So there's like no hope of like actually separating them in the real world, right? Because then we'd have a proof that P is not equal to P space, and that's really hard. So let's give up on that goal for now. Can we at least separate them relative to an oracle? So this has been tried for many years, and I guess more than a decade, and there's still no known oracle separation relative to an oracle in the usual sense of the term. So yeah, no oracle that decides some language. So what is today going to be about? It's going to be about a generalization of the usual notion of oracle. And we're going to give you a model of oracles that arguably is pretty close to the usual model. And I'm going to show you a separation there. But first, let me review what's known in the setting of like generalized oracles. So the first people to consider this question were Aronson and Cooperberg in 2006. They defined a model called a unitary oracle. I'll define these models all in a second, more precisely. And they showed a separation there. In 2015, Pfefferman and Kimmel showed a separation in a more restricted model of oracle. So all of these are like more general than the usual classical oracle. The unitary oracle is the most general. Pfefferman and Kimmel had something less general, which is what we could call a distributional in-place permutation oracle. So I'll define that in just 2 slides. And then this work is a distributional classical oracle. So it's almost the same as a classical oracle, but with a little twist, this distributional thing. And that's sort of the best known so far. And it would be really great if someone could remove this distributional thing and we get a classical oracle separation. OK, so in the next part of the talk, I'm going to tell you about these oracle models, try to motivate what we're doing, and then I'll tell you about the result and its proof. OK, so what is an oracle, right? So the idea, like when we define an oracle, the idea is that we get a black box that solves some computational problem at unit cost, right? So like when you say you have an NP oracle, it's like you imagine it's like a box that you feed in any 3-set formula, and it tells you satisfiable or not satisfiable, right, in unit time. So classically, that's pretty easy to model. It's just like you have a box that executes this map for some function f that's like the computational problem that's inside the box. It takes an input x, and it maps it to f of x, right? Very straightforward. Now, how would you take a classical oracle defined like this, like an oracle for 3-sat, and use it in the quantum model? So the first thing that you might think of doing is like, well, I know in quantum I'm supposed to map states to states instead of bits to bits. And maybe I know that in quantum, like all the maps are unitary matrices. So what I should do is write down a unitary matrix that maps x to f of x. So this is not the right definition, because for many reasons. One of them is that, like, in general, f is not a reversible mapping, right? It could be like for 3-sat, for instance, f was a Boolean function. It was just telling you, are you satisfied or not, satisfiable or not. And so there's no way that this map could be reversible, but all unitary matrices are inherently reversible because they have inverses. So this doesn't even make sense. So it turns out the correct thing, or at least the standard notion that people use in this field, is the following. It's a unitary that takes in an input and then an output register that you can initialize to whatever you want. So I've written down y here, but just imagine that y is 0. That's the way you're supposed to use this object. So you give it an x and 0, and it's going to give you back. It's going to maintain x in this input register, but in the output register, it will write down the value of f of x. And now I've written this for general y to show you that it's a reversible transformation. So for any y I put down here, I just XOR the value of f of x onto y. And this is like manifestly reversible because if I just do the same thing again, like I apply this twice, like the XOR will vanish and I'll get back xy. So not only is this reversible, it really is, I think, natural for the following reason, which is that you wanted to say that like your Oracle model should make sense and that if someone actually gave you an algorithm to compute the problem inside the Oracle, then you could actually instantiate the thing you have, right? So like if you code to compute f, you could plug it in, you'd get something. So it turns out that if I have a classical circuit for f, this automatically gives me a quantum circuit that implements this use of f. Like you just take your classical circuit, you convert every gate into a reversible gate by the usual tricks, and just run that coherently, and that's your use of f. So that's why this is kind of the gold standard definition, I would say. OK, so this is what we want. We do not have a separation for an Oracle of this form. What is known? So first I'll tell you about the previous works. So the most general class of Oracle, this is the first result by Aronson and Kuperberg, this is what they call the unitary Oracle. So here they just allowed the black box to implement any unitary matrix at all. Not necessarily computing a function that you could describe classically in any way. And this made their Oracle separation kind of a lot easier to achieve. So the particular unitary they used in their black box was just the reflection about a particular hidden state. So you plug in the hidden state, it acts on it with a phase of -1, and for everything orthogonal to that, it does nothing. So then you can just by kind of like counting arguments and ideas from like the Grover search lower bound, you can show that you need to make exponentially many queries if someone doesn't hand you a copy of psi. Like there's no way you could find it without being given it. But this kind of is a little unsatisfying. Like it doesn't tell you much about like the classical Oracle world because this is too different from how a classical Oracle behaves. The next improvement was this result by Pfefferman and Kimmel. So remember I had the word distributional. I'm just dropping that for a second. I'll come to it in a bit. But let me tell you what they had. So they had an in-place permutation Oracle. So this is less general than any unitary. They said that the black box U is a unitary that happens to be a permutation matrix. So every permutation matrix is a unitary you can check. So on input x, it will just map it to some pi of x, where pi is a permutation. And crucially, they said that in their lower bound, they said you have to have access to pi, but you are not allowed to have access to pi inverse. Like their proof would just not work if you had access to pi inverse. There'd be no lower bound. And I think this is a little bit unreasonable because if someone gave you an instantiation of pi, like a circuit that actually implements this unitary, then you would immediately have a circuit for pi inverse because you just take the circuit and run it backwards.
So it's kind of like a classical one-way permutation kind of thing?
Yeah, well, yeah, that's right. Yeah, because like you can do the permutation, but not its inverse. Yeah, that's basically what it is. Yeah, and somehow the separation is like quantumly you get a superposition on the pre-image of some set, but like classically, there's no way you could construct that yourself because you can't invert the permutation. Okay, so that's what they did. Now, what did we do? So here is our model. So our model is basically, it is the classical model. So the one that has an output register and it writes the output by XORing, but with the following catch. The catch is that instead of having a fixed function f that the Oracle implements, the function f is actually sampled from a distribution, script b, and the sampling only happens kind of at the runtime of the verifier. So in this Merlin-Arthur proof system, when Merlin is coming up with his witness to send Arthur, Merlin does not know which f is going to be sampled. He only knows the distribution that it's coming from. So that's the catch here. And you can imagine this could maybe go both ways, right? Like maybe it makes it harder for Merlin to come up with proofs, but maybe it also makes it easier to constrain Merlin's actions. So for us, it turns out that the latter effect is more important. Like it makes it much easier to argue about the things that a cheating Merlin could do. So you could just like a picture, just saying the same thing that I said in words. That like the prover Merlin does like picks the witness depending only on the distribution, and then the verifier samples an instance from the distribution and runs his algorithm for that particular instance. So what's called X there is really F. So this is valuable in our techniques, like in our proof, because it lets us assume that Merlin's witness C depends only on this distribution, not on the F. That's going to be useful. I'll discuss that when we get to the proof. But it's definitely not a natural assumption. It's not at all natural. The one thing I can say in its defense is that Pfefferman and Kimmel also had to use exactly the same kind of assumption. So their in-place permutation oracle was also distributional. So at least we're not worse than them. Clearly, like the big open question here is to get rid of the distributional part. But that seems like it might require new techniques. Okay, so hopefully at this point it's like clear what the oracle model is that we're going to show a separation in. Are there any questions about that? Okay, I'm not. So okay, now let me tell you the result. So the result is basically what you would expect from what I said. We show that there's a family of distributional oracles, like indexed by some size parameter n, and a promise problem such that there is a QMA to the U machine that solves this promise problem in just one query to the oracle. So given the right proof, it makes one query and it will accept the yes instances with a completeness probability of 1, so with certainty. And for every no instance, it will accept with probability at most 0.01. Now, the other part of the theorem is the lower bound on QCMA. So we show that no QCMA machine with access to this oracle U can solve this problem with completeness better than 0.99 and soundness less than or equal to 0.01. So you might wonder, why do I have explicit constants here? Well, unfortunately, like the usual amplification techniques for QMA and QCMA don't work in the setting of the distributional oracle. So like the choice of constants matters a little bit. So what we show really is that there is some set of constants where you get a separation, right? But if we chose different constants, then maybe you wouldn't get a separation here. But I still think it's reasonable, right? It's interesting that you can get this for any choice of constants for the completeness and soundness. Yes.
With how many queries?
With polynomially many queries. So actually, that segues right into the next bullet point, if the clicker wants to do it. Yeah. So in general, we have this comes from a query lower bound that's saying that any quantum query algorithm that gets a witness and makes queries must either have an exponentially long witness or an exponential number of queries. Oh, it probably could be made smooth. I mean, we didn't really care about either of them being super polynomial, right? So, yeah.
So maybe anything. So you mean even if Q times T equal to exponential is not enough? If you have 2 square root of exponential equals to T?
Oh, wait, so you're saying that oh yeah, I don't know if we can show directly that Q, I mean, I guess this implies that Q times T is exponential, right? So that's, yeah, that's true, yeah. No, I mean, okay, sorry, when I say exponential, I mean 2 to the n over 100 or something, right? It's not yeah.
Both cannot be exponential at the same time? Because the mass
Sorry? Oh, yeah, they could both be exponential. Yeah, I mean, but okay, it's kind of clear that with either one of them exponential and the other one polynomial, you can solve the problem, right? If T is exponential, so this is just a query algorithm at this point. There's no runtime constraint. if t is exponential, then you can just query the oracle everywhere and you extract the whole instance and then you've solved the problem. And if q is exponential, you can get like a complete description of the QMA witness. So yeah.
But there is also distribution, right? So another issue. Okay, so Q is okay. So T is exponential, that's obvious, but Q is exponential, then there is also a distribution over B. So
Oh, good. Okay, we'll get to that in a second. It turns out there's a unique, so in the QMA protocol, there's actually the same witness works for everything in the support of the distribution. So yeah, so you could just give a description of that witness. Okay. So now let me tell you what the problem is, and then we'll see how much of the proof we can make it through. So the problem is kind of a graph connectivity problem for random graphs. So, so I'll just define a graph here. So we'll say G is a deregular graph on exponentially many vertices, where D is, I believe, a constant. Yeah, I think it's a constant. It's not that big. And you think of this as a union of D perfect matchings. So like, in other words, each edge is kind of like colored with a color from 1 to D. So okay, this is in my terrible keynote drawing skills. This is like what the graph might look like, so with like 3 colors. And the oracle gives you the colored adjacency list of this thing. So it's like, but what does that mean? Well, if you plug in a vertex and a color, it spits out the neighbor of that vertex along the edge labeled with that color. So now what's the problem that we're trying to decide? We're promised that either we're in the yes case or the no case, where the cases are as follows. So in both cases, we're promised that all the components of the graph are spectral expanders. So like each component, its like second eigenvalue is small of the Laplacian. And in the yes case, we furthermore have that the graph has many connected components, like actually kind of an exponential number of connected components. And in the no case, it's connected. So this is like what the yes case looks like, and that's what the no case looks like. I'm going to decide which is which. Okay, so that's the, these are what like the graphs look like. And I have to tell you what are the distributions that are going to define instances of this graph, of this problem. Here are the distributions. I'll just tell you what the yes distributions look like. The no ones are actually, like, you can sort of pick whatever you like. But the yes distribution will be, we pick a random graph subject to the constraint that all the components are expanders, and also subject to the constraint that a fixed subset of the vertices forms one of the components. So we fix a subset S, and we condition on that subset being one of these n to the 1/10 connected components of this graph. And the rest, you know, the edges within the component we get to pick randomly, and like what happens outside the component we can do as we wish. So here a yes instance, as in the distribution that yes instances are sampled from at runtime, is fully specified by the set S. That's going to be important later. So that's when Merlin gives you a proof, that proof can only depend on S. It cannot depend on any other information. And in the no case, really you can pick whatever you want. Like you could even have no randomness at all in the no cases. They could just be fixed graphs. Okay, so this is now the problem. So now let me tell you, why is this in QMA? Why is there a protocol in QMA? So why is it in QMA? Well, it turns out that with this colored adjacency list oracle, you can actually do walks on the graph. You can do a random walk on the graph. Because like the nice thing about the colors is that like once you move, like you compute from V comma C to like V comma C and then the neighbor, because the colors are kind of reversible, you can now erase the register containing where you came from. Like you can, from the neighbor, you can uncompute V. And this is very important for doing a random walk. Like you can't remember like where you came from if you want to like produce a distribution over the graph. But it turns out you can do this, so you can do this random walk on the graph. So then once you have that, you can kind of do the following protocol. So I'm given a quantum state by Merlin. I will do I'll do both of the following checks, actually. So the first check I'll do is I'll check that the state C is a +1 eigenvector of the walk unitary, which I'm promising you this unitary can be implemented using the oracle. And how do I check this? Well, this is like one of the standard algorithmic primitives in quantum. It's called phase estimation. So here you just want to check whether something is 1 or not. So there's actually a very simple version of this, like 1-bit phase estimation. So you can do that. And now, so you check that. So this tells you kind of that C is an eigenvector of the graph Laplacian. That's what this is telling you. Now, the other thing you want to check is that the graph was disconnected, right? So when a graph is disconnected, it has a degenerate 1 eigenspace of the Laplacian. Like the all ones vector is always a 1 eigenvector of the Laplacian for a regular graph. But here you'll have things that are orthogonal to that also have eigenvalue 1. So we just have to check now that this C, which I already checked as an eigenvector in the first part, is orthogonal to the all ones vector. So that's the other check, and this is easy to do with the quantum Fourier transform. Like you just take the Fourier transform of C and measure it and make sure you don't get 0. So in the yes case, you're guaranteed to succeed with certainty if you get the right state C, and this is just the eigenvector that's orthogonal to the all ones. It's kind of, you just flip the sign on like one of the components and weight them appropriately. Like that should be familiar if you've done like spectral graph theory. And in the no case, no witness can succeed because of the spectral expansion of the graph. Like in the no case, remember the whole thing is just one big expander with spectral expansion. So there's a unique +1 eigenvector, which is the all ones thing. So anything you send that passes the first test will be rejected in the second test with a decent chance. So that's the containment in QMA.
So where do you use a lot of components?
That was not used yet. So that's going to be somewhere in the QCMA lower bound. Like it doesn't matter at all for QMA. Yeah, good. Okay, so I think in terms of time, I'm not going to make it through this whole proof, but I can hopefully give you the outline. So why is it not in QCMA? The starting point for our proof is that this problem was considered in the BQP setting, so the setting where there's no Merlin, by Ambinus, Childs, and Liu in 2011. And they showed a query lower bound here. So they showed that if you have no witness, you need exponentially many queries to the oracle to distinguish even like one component versus two components. So now the whole business that we have to do is like when there is a witness, we have to show that this bound still holds. So to kind of get rid of the witness somehow. So the strategy is like, so the first step is kind of a standard step in like QMA, QCMA lower bounds, which is you try to fix a witness. So you say, look, for every instance, there's some witness that's optimal for it. So let's just say, there is a witness that's like optimal for some set of instances. And we're going to pick this set of instances appropriately such that the ACL, I guess it's, archive versus publication, ACL, whenever paper holds even if we only have instances drawn from the set D rather than overall instances. So it's like the super high level outline. Now for a slightly lower level outline, the first step we do is we'll just like pick the witness that's optimal for the largest number of instances. Every witness is like optimal for some instance, or maybe it's optimal for nothing, in which case it doesn't matter. So, but just by counting, there are many instances have to map to the same witness because these witnesses are only bit strings, but the instances are exponentially big graphs. So there's got to be one witness that's going to be given to you by Merlin optimally for many, many, many different graphs. So let's just fix that one, and we'll look at all the graphs that work for this instance. Now what we do is we show some kind of like combinatorial properties of these graphs. We show that they all kind of have overlapping sets S. So remember, S was like the thing that was supposed to be one of the components. Like all these components have to kind of overlap on a decent fraction. So that's an object that we call a sunflower. And yeah, so we have this sunflower. And then the remainder of the proof is kind of saying that like, the algorithm has to work now if you just pick instances drawn from the sunflower rather than all instances. Now, the remaining steps are kind of like, first, this distribution of like picking things from the sunflower is a little hard to analyze. So we first modify it to look a little smoother out. So we change it to this like pink round thing. And we show that that's computationally indistinguishable from the sunflower. So that's done by the adversary bound, if you know, quantum lower bound techniques. So it's kind of, this problem is a good fit for that because like the adversary bound likes Hamming distance, and like there's Hamming distance bounds you can show here. And then step 2 is to show that this pink circle distribution is hard for a quantum algorithm with no witness now, because the witness has been hard-coded up to this point. And this we do by kind of tweaking the ACL10 proof. Like they use a technique called the polynomial method, which is good for very symmetric sets of instances. And now this like pink circle is like very symmetric because it's a circle. So yeah, so we can make this work. So that's the proof in a nutshell. So now maybe I will not say too much about these open questions, except the first one is like, obviously we want to get rid of the distributional assumption. There's like other questions that are like related to advice classes, and like I will say there's like a work that came out after ours that kind of showed the same separation but with a very different technique, like using the Yamakawa-Jandry problem. So can we merge our ideas somehow? But maybe I want to end with this slide here, which is that there's kind of a connection between this whole question and quantum money. Like not an entirely formal connection, but I think an interesting one. So actually our problem, this like graph problem, is not original to us. It came from this paper by Ludomirsky from 2010. And so he basically defined like an abstract problem that kind of fits our graph thing. But his motivation was a little bit different. I think it was for thinking about constructions of quantum money. So basically the idea he had is like, you might consider states that are like a superposition over a single component in the graph to be a money state. And under some conditions, you can maybe hope to show that these are hard to copy. So like you can't counterfeit the money. But there's like designing like public key quantum money is like a big open problem. And so it's just like interesting to see if we can get any inspiration from here. So I think that concludes what I have to say. And thanks. Yeah.
The Yamakawa-Jandry separation sort of like shows this total search problem, right?
Yeah.
And get an exponential separation. Can you say something about like how this even relates into QCMA and QMA, which are like decision problems?
Yeah, so they like encode some other problem with the Yamakawa-Jandry thing. It's like you have to, okay, the first observation is like in Yamakawa-Jandry, you don't need to make any like live quantum queries to the random oracle. You can just have like all the information baked into some advice states. So these will turn into like the quantum witness state that Merlin has to give you in QMA. And you won't have this in QCMA, so you won't be able to run the Yamakawa-Jandry algorithm. And then like the problem you want to solve is just like there's some like hidden string inside the oracle, but to get at it, you have to first solve the Yamakawa-Jandry problem and then like query the oracle on the solution or something.